So today we are going to talk about Chern class, and at the end maybe a little bit Lefschetz 1-1 theorem. But let's see how far we reach. Okay, so as usual, X a smooth projective variety over C. Then here we will need to use the analytic topology, or this usual topology of X. So I will write Xn for analytic. So there is a very well-known short exact sequence. Maybe I write this. What was? Just a moment. So this the sheaf of holomorphic functions in Xn. So when I am writing this Xn, this means that this is the usual topology. So these neighborhoods are small; they are not Zariski open. So we have this exponential function. Let's say maybe O star Xin, maybe. Okay, what is this function? F going to the EF, and O star OXNAI is the sheaf of holomorphic functions without zeros, or equivalently the sheaf of invertible holomorphic functions. So it turns out that this is in the sheaf theoretical context, this is surjective. Why? Because even you have small open sets inside Cn, and you have a holomorphic function f, then always we can take the logarithm of this guy, f log. Oops, once again I am messing up. Then we can take this log f. For example, if this is a ball, there is we can always define log f, which is one valued function. Okay, so since locally we can take log of holomorphic function, this is a surjective map, and what is it's a kernel, and we know that it is kernel. It's just z. Sometimes we want puts here e to the 2 pi I f, but for some reason I didn't put here, so the kernel will be 2 pi I z with the additive structure, and then 0. So this is a very important short exact sequence that it appears in many, for example, Lefschetz 1-1 theorem in the modern proof. And so you have to carry in mind that this is a morphisms of abelian group. The structure here is addition. The structure here is addition, but here the group structure is multiplication of function, because addition goes to multiplication here. Anyway, once you do this one, then something that we learn in algebraic topology, that any short exact sequence we can construct a long exact sequence. Maybe I write the long exact sequence, H1, let's say Xn and star. I will not just this from this side. Okay. Oh, sorry. Again, I'm making a mess. There is no 0 here. So we have H2 Xn, this O Eraser. X and a star, and later I will need also to consider this map. Let's call this map C. This is a co-boundary map, and the inclusion map I will need also. Let's rename it H2X and OX. Sorry, I'm making again a mess. This is not. This is 2 pi I Z, and then there is an inclusion. Okay. So we will have this co-boundary back from H1 to H2 here, and then the map P inclusion. So this is our Chern class map, and this is actually it is also sometimes called first Chern class. And yeah. Okay, I need to write down this this map explicitly in algebraic de Rham cohomology. So the point is that I have also a map from here to algebraic de Rham cohomology. Let's for the moment consider the analytic one. So this was H hypercohomology of X and the complex of differential form on X analytic. So in some sense, what we want to do, we want to understand what is this map. I will call it also again this C. And the point is that once we describe this map explicitly, then we can replace analytic with algebraic, because we can talk about this guy in the algebraic framework and so on. In the same way, we have algebraic de Rham cohomology. So the idea is that to see at the end what is this map in our algebraic context. So let's try to decipher what this C. I think. Okay. Okay. So let's. So the proposition that we want to see is that if these are called line bundles, but later we will see why what they are called line bundles, the element of this guy. But at the end of the day, the elements in H1 is given by Hij. So let's take a good covering, and Hij are OX and a star UI intersected with UJ. And okay, so if LA, then this guy is in my so something maybe let's say this is also called Picard group of let's say Xn. Later we will find out the algebraic. So this, if you have this elements in Picard group, then C this Chern class, the Chern class with values in algebraic de Rham cohomology is given by. So remember that an element here in principle contains the differential 0 form, 1 form, 2 form, but it turns out that in our case it is just DHIJ in a proof it will be clear. Hij in okay. Now I will show you what it means here. Actually, in the case of the polarization, we had already seen this map, but we see it here once again. Okay, so what this is not definition. This is actually. So maybe I remember. So any element here, remember that it must have a zero collection of zero form, one form in the double complex, and two form. And the formula says that here we have zero, here we have zero, and remember that omega 1 it is defined where in the intersection of it is a one form in the intersection of open set. So in our case, this omega 1 is just this collection of DHIJ HIJ. So this means that it contains this algebraic theorem cohomology just contains this one form in its expression. But if you have already seen a Chern class, remember that the Chern class it lives in the second cohomology. So in the C infinity context, it is a C infinity two form. But in algebraic context, it will be just this collection of holomorphic one form. Okay, so let's go to the proof of this fact. In order to see the proof, first you have to remember this co-boundary map. So you have to remember. Oops, it is okay. This co-boundary map, how it is constructed. But maybe in order to save a little bit time, I will say it explicitly here. So, so you have this. So for the co-boundary map, what we do is that first you have this UI, you have this UJ, and locally you have this HIJ. Then first you take a branch of the logarithm if in the intersection log. So you define Gij log Hij, and at the end this C, the first C, what I'm saying that this first C that we define XAN, this is the co-boundary map, is given by delta Jij, delta the cohomology element, and remember that this is just just let's say actually delta J. So delta J, the J will be the collection of this Jij, and delta J in the intersection of three open sets. So we have to take three open set, UI, UJ, UK, and so delta IJK, it is just GI, what was the formula? First I remove the first one, JK minus JIK plus then the last one, GIJ. And okay, so if one of the things that in the course of algebraic topology last semester I did, whenever I there was some co-boundary map, I asked the student to write down the co-boundary map explicitly. This is one place that one might try to understand the co-boundary map. So in this case, you have just take the logarithm. Of course, in each intersection, you have to choose the branch of the logarithm. For this reason, when you choose in here, and let's say 3 times, this here, and then this here, and then the other one here, then you have when you make this sum, it will turn out that this is in 2 pi I z. Okay, this is the classical. This is just choosing the definition of the co-boundary map. But now we want to translate this one to algebraic theorem cohomology. For this one, we have to go to the definition of algebraic theorem cohomology. Maybe I will let me write in our double complex. Maybe I make this picture now. So this will be these places for me. In the double complex, remember, let's make this picture. This will be computed. This will denote the elements of H2, hypercohomology H1, and then hypercohomology H0. Okay. Okay. First of all, this CL, that's the CL that we have here, it is here. So let's call this one denoted by Cijk. Okay, this is we have our Chern class here, and of course here we have 0 forms which are holomorphic, but constant functions are also holomorphic function. So at the end of the day, if I put Cijk here, 0 here, 0 here, then this is an element in of H2, because its D is 0 because the Cijk are there. Its delta is equal to 0 because it comes from the Czech homology. But now I have to modify this one to get something in the let's say something in the algebraic. I will take another equivalent element in H2 for the Cijk. Okay, what is this? So the point is that I want to get rid of Cijk because they are defined in the analytic topology, and I want something that at the end it might be possible to replace it with the Zariski topology. So the point is that the Gij, this Gij is here. Okay, so my G is here. So I will take D of this guy, this difference. So remember that D was delta plus minus 1 J D, and G did J was referring to Czech cohomology index. Cohomology index. So in our case, so I want to apply this DG. I want to apply this DG. So G is let's here which place we have. This is the let me see. This is the this is the place we have a 0 form in 1. Let me exactly here. This is the, let's say 0 form. That's in the shift-theoretic language. Remember that this is the S01. So the Czech homology place is or not. This is S00, S01, S1. Yeah, that is okay. This is S01. So this means that at the end of the day, dg is for what is delta g minus of d of g. Yeah. But let's see, delta G is what? Delta G is, so I want to modify these elements of the hypercohomology by adding some exact form. So I want to add this one to Chern class. So this means that dg, so maybe continue this one. Delta G is what? Delta G is exactly this CL. And what is dg? G is the logarithm of Hij. This is dHij, Hij. Anyway, when I add, let me see, dg, okay, maybe in this way. So C, maybe I have to really, for the argument, distinguish between the topological and algebraic. So let's call this one top, because both with T top, I will call it. So topological, and then topological. Okay, so now T top, topological, L minus dg is okay. Let me see. I want to get rid of. I want to make dg plus. But what I want to do. Okay, no, let's do. C top L minus dg is equal to dhij. Yeah, it's just rewriting, nothing more. So anyway, C topological minus some exact form is this one. This means that at the end, I can define C, this algebraic, let's say Chern class, just a bunch of this differential one form, because this guy and this guy in the hypercohomology, H2 hypercohomology, they are the same, because this capital Dj is equal to 0, and then the proposition improved. Okay, what is the moral of the story? The moral of the story, maybe I return back to this the first page, that the topological Chern class that that lives here, you cannot take it into Zariski topology, because this actually in Zariski topology, these check cohomologies, they all 0, and these cohomologies are non-trivial if you consider the analytic topology of XX. But so this means that we cannot translate our Chern class to algebraic one directly here. Then the modification, when we do modification, then algebraic Chern class. So this is algebraic Chern class. It will be this expression. Okay, so this is one thing. Any question? Okay, so let's go to okay, so let's go to the algebraic side. H okay, xn xn. Okay, the point is that this Picard group is the same as when you consider in the algebraic framework. And you cannot directly apply this Serres-Gaga principle here, because these shifts are not coherent. And actually, today was thinking of this. But anyway, at some point I will explain why these considering Picard groups in analytic topology and this in Zariski topology, they are the same. And when we have these notations means that we construct this H1 by Zariski open sets. So when we are talking about Hij here, this means that here the Hij ui is covering with affine open sets. Okay, and at the end of the day, we have we just translate our Chern class to this algebraic context. Okay, there is one natural way to construct line bundles is before I proceed, I have to announce something. In the previous lecture, in many proposition, I had to assume that Z is irreducible because I was doing the singularization, and I was assuming that the top cohomology is one-dimensional. So one starts with irreducible one, and then one proceed everything with non-irreducible one, writing as a sum. Okay, so this is one point that I had to remember. Okay, so let's go. So let's Z. One of canonical elements that we get here are obtained by divisor Zi irreducible subvarieties of subvariety of X of codimension 1 of codimension 1. So we plan to give the idea of the proof of Lefschetz 1-1 theorem, which is about algebraic cycles in codimension 1. Okay, so and as you said, I will take this this covering in each open set UI. Z is the divisor of a rational function. So anyway, this is since we are in affine variety, so this means that let's say there is Fi, a rational function Fi. So let's divisor Fi is just let's say Ni Zi looking in this UI. I may have made too much I here. Let's just a moment. Maybe I take this one K equal to 1 until S, and this is K, and then I reserve I for the covering. Okay. Okay, this is K equal to 1 until S. Anyway, when you have divisors, let's say Z1, Z2, Z3, and then you have this, let's say, multiplicities, N1, Z1, N3, Z3, let's say here N2, and to any point you take here, then basically you take the equation of let's say this Zi. So if Zi is given by let's say G, let's say the K equal to G, K equal to 0, then you just define a F product of GK to the NK, and K equal to 1 until S. Anyway, the good point with codimension 1 varieties is that they are always given by one equation. And actually, why the Hodge conjecture in codimension as 1 is easy is comes from this simple fact. Whereas when you go to codimension 2, 3 subvarieties, always you need more equations than the codimension of the variety. And that's one of the reasons why the Hodge conjecture in higher codimension is more difficult. But anyway, in codimension 1, you can write the equation for your divisor. So you can define this line bundle LZ. So I want to define this LZ and H1 X. Let's call this one peak of X, to emphasize that it's algebraic peak over X over C. So LZ in peak X. And okay, so what we define it, of course, when you take Fi divided by Fj, let me follow it. Okay, Fa divided by Fj. When you make this quotient Fa divided by Fj, all the zeros and poles disappears, because Fi and Fj at the end they have the same pole and zero. So the poles and zeros disappears, and then you will get this Hij, and which Hij is in X Ui Uj, invertible one, because I said this making this quotient the pole and zero will disappear, and then at the end you will see that at H is Hi, you can define Lz Hij. This is really an element in Picard group. Picard group of X. And it is easy to see that this is in the Picard group. This is the differential, let's say, delta of this one is 0, because Hij's are in this format. So what I'm saying, Hij, Hjk, in the intersection of three open set, Hki, this is 1. And just because use this one. But it is a non-trivial element because we cannot write down Hij in this format with Fi's invertible. If Fi and Fg were inventable, then this element is 0, is the identity element in the Picard group, but it's not the case. Anyway, for any divisor, we define element in the Picard group. And okay, so let's go further. One proposition that it's a kind of embarrassing again, that I would prefer to have algebraic group, but the bad reputation of Hodge theory is that it has a lot of algebraic statement, but at the end the proofs goes to functional analysis, to harmonic analysis, and so on. And anyway, let me write one of these propositions. So the proposition is simply this one. Remember that we defined this element. Defined through this singularization of Z, etc. This is the previous lecture. But from another side, we have another element, the Chern class. which is also here. So the proposition is that these two things are the same. And since Monday, I was really I tried to see if it is possible to improve a little bit the available arguments in the literature in order to give a algebraic proof. But still I'm far from. But what I'm saying that even you can put here arbitrary field, you can be of character 0. You can define it here for arbitrary field, and then the same way the Chern class also you can define it for x over define over arbitrary field of character 0. And so a priori one might ask purely in a proof in algebraic framework. And well, the point is that the proof so one has to go to check cohomology or to C infinity de Rham cohomology. And the one proof that I am aware of is the Griffiths' Harris book, this Principles of Algebraic Geometry, let's say page 121. Okay, so this uses prove the same statement in C infinity de Rham. Prove this statement in C infinity de Rham cohomology. And at the end he used integration. So for this one you just need the classical the topological Chern class, and then in this infinite de Rham cohomology you can actually you can avoid the desingularization. As I said, integration of forms over Z is the same as integration of the forms over the smooth part of Z. And then the proof is done. Maybe next week Felipe will talk about some classical presentation of the Hodge conjunction, and the week after the next week Felipe talks about this proposition in Griffiths Harris book. Anyway, since I don't have really algebraic proof for this one, I will skip this one. So we will have exposition of this Griffiths Harris's this proposition in Griffiths Harris book. Okay, so let me assuming this one, then we have already our Lefschetz theorem. One. In the way that I am presenting, you will not see 1 because this has to do this PQ form, C infinity form. But at the end, this is the Lefschetz theorem, and actually I will present the Lefschetz 1 theorem in the original format using integrals. Okay, let's write the theorem and try to prove it. So X is smooth, projective. What else of dimension n? Then delta h2n minus 2 x. So here we have to go to analytic Hodge cycle. So remember that in our definition of a Hodge cycle, That is, maybe I always mess up with indices. What was the Hodge conjecture in this case? It was just F integration of some piece of the Hodge filtration of H to n minus 2 theorem X. Here you can take the algebraic one, because the idea is that we want to integrate only algebraic object. But it was then the way this divided, it was 10 n minus 2. This is Fn in this context. Okay. Then delta is algebraic. And what is this? This means that delta is the homology class of, in this case, the dimension of 2n minus 2. This at the end it will be, let's say, I equal 1 to k, zi inside x codimension 1 sub varieties. And if you want, since we have already written as sum, let's say irreducible, let's call it irreducible subvarieties. So this is the Lefschetz theorem. This means that at the end, the Hodge conjecture is true in let's say 4 divisors. One moment. Okay, so basically the proof, the main part of the proof is this statement that we have not proved, but let's proceed. Anyway, one of the reasons why this lecture notes with Roberto, I want to make algebraic proof, because I think this is a kind of always tendency in the complex algebraic geometry and topology of topology, that one wants to push the things into purely algebraic statement, because in some sense the purely algebraic statements and proofs, they are much more rigorous and one can trust more on these proofs. Whereas always topological proofs, they are very intuitional, and even so one enjoys reading topological proofs, but the level of rigor sometimes is less than algebraic proof. Anyway, let's go to the proof. This part of the lecture I just wrote yesterday, and I will update my lecture notes in the web page just today. So if you want to read from the text, be patient. Today I will update my lecture notes in my web page. Okay. Okay, so let's go to the proof. First of all, well, the proof actually goes through going to cohomology, and this Poincare dual of which is in H2, let's do X, H2X analytic Z. Maybe, okay, what is the Poincare dual? This one I wanted to mention earlier. The Poincare dual is basically uniquely determined by this equality. Cup. So in this case, omega, this is the whole variety X analytic, and then omega for all omega in H2 n minus 2 the Rama X. Okay. Well, as I said, I for dealing with this one, I can consider the algebraic one. Anyway, when you do so, this determines the Poincare interval uniquely, so it is in H2. And well, maybe I have to say that the proof will be up to some 2 pi I factors. And actually, this 2 pi I, this is the main reason why I have not up-to-dated my lecture notes in my webpage, because there is a mess of some place must appear 2 pi I. I have not written. But anyway, the proof, let's consider the proof up to some 2 pi I factor. So this means that it might be some 2 pi I here or not. Okay, so it turns out that when you go to the cohomology, delta PD is in H2X, let's say analytic Z, intersected with let's say F1H H2 the Rham X. If you want, let's push in the analytic context. Yeah, I think it doesn't matter if this is analytic or algebraic. Anyway, you see that there is, so the point is that we have this map from H2X N Z to H2 theorem X, and this map kills the torsion. And actually, by this, I mean that the image of this guy under this map. So either you take this one, the image of this here, or up to torsion. Maybe you just consider this one up to torsions. Okay, maybe before now we talked about torsions, I have to say one comment here. That okay, about the definition of Hodge cycle. So by our definition of Hodge cycle, any torsion class is a Hodge cycle, and any torsion class is a Hodge cycle. And at the end of this Lefschetz 1-1 theorem, it says that even any torsion class will be the supports of an algebraic cycle. And this integral version of the Hodge conjecture, it's called integral Hodge conjecture. So actually we are claiming that the integral Hodge conjecture is true in this case. And the way that announced with the actual Hodge conjecture, it was over rational numbers. And the reason is that integral Hodge conjecture in general fails. But I wanted to mention that at the end, in our context, the torsions, this will be just 0, and the 0 is, we will see that it is algebraic in our context. Anyway, so let's go forward. It is we can easily verify that this guy will land on F1, and actually this is the classical definition of the Hodge cycle, which is, in this case, let's call it Hodge class. Maybe I make some remark. The Hodge class in general, H M X analytics Z, let's say F, when M is even, M half plus 1 of HM the Rham. Oh no, sorry, this is just a half. Where is my eraser? Of the Rham cohomology of X. So the classical Hodge cycle or Hodge classes, they are in the intersection of this lattice with some piece of the Hodge filtration. Okay, let's go forward. Okay, so delta, maybe let me call this one alpha now. Alpha. So at the end we have it is in let's consider an H2 theorem X, and then we have this. Remember that this guy has the Hodge filtration F0, F1, F2, and the other, there is just these three pieces, and then we have this projection F0. F0 is the whole theorem, cohomology of F0 divided by F1. And okay, maybe I write this. And from F0 to F1, we have also a map to H2 X O X. Yeah, okay, so let's say. So first we take this quotient map from H2 to just quotienting F1. And we have also this map. Actually, this map is isomorphism, but we will not do this map. What is this map? Remember that the elements here, omega here is given by, in the double complex is given by this kind of 0 forms, 1 form, 2 forms. F1 contains these elements. So this F1 contains these elements such that this guy is 0. Okay, so this means that and the map that I am defining, this is just taking omega 0, omega 1, omega 2 to omega 0. And this is a well-defined map because remember that the d of this guy must be 0, but d consists of delta and d. And here there is just contribution of omega 0. This means that the delta omega 0 is 0. This means that the end omega 0 defines a well-defined element here. So this map is well defined, and I mentioned that these maps are isomorphism, but for our proof we don't need this isomorphism. So, but at the end of the day, what we get, we have this, let's say this map H2 theorem X to H2 X O X. Let's call this P check, and our P check alpha goes to 0 because alpha is in F1. Okay, so now we reach to the beginning of our course, where it was. Remember the long exact sequence of this short exact sequence, and there was this P map. And there was this P map, and it was defined by cohomology with Z coefficient, but then we took it is here. Then actually we have this, let's go, actually then I have to call not this P map, okay, not this P. And and okay, so this P map we have here. So that P map we have defined in the, let's say, analytic. It can be defined also in the algebraic framework. So let me write. Then we have H2 theorem X analytic, H2 X analytic, X analytic. You have this map, and well, by Serre's Gaga, all these things are the same. I mean, the cohomology of coherent sheaves and even the hypercohomology of sheaves of coherent sheaf, complex of coherent sheaves, then you will get the same things. And then we claim that this P is the same as P check. And the reason is a kind of trivial. Okay, this not trivial in C infinity context and Hodge filtration given given by PQ forms. And actually, this is another proposition in Griffiths-Harris. Let me see which proposition was it? Okay. Okay, I have. Well, anyway, this is next week. Philippot will talk about the classical version of the Hodge conjecture using PQ forms and so on. But in this context, it will well, at least in Griffiths-Harris book, one takes some 1-2 page to prove this. But in our context, this is easy, and the reason is this. Okay, I have more. Let's go to the proof. Okay. Okay, the reason is this one. And so first of all, we have the let me say first of all what we have to do we okay. So the point is that this one is given by the let me see what I have done. H2 theorem X H2. Okay. Actually, let me go to not write in this way. To go back to the original P. I made the original P was in H2 Xn, and then this Z map. And as I said, still I have to fix this 2 pi I. Let's put 2 pi I Z also here. 2 pi I. Okay, so let me a little bit clean here. So I had my alpha here. I have my alpha here, and look at alpha, let's say here. It goes to 0 by P check. I want to say that it goes to 0 by P also. So I have to see that this diagram commute. So in some sense, let's take here C coefficients, multiply it with tensor with C, and then we have isomorphism again here. And yeah, I think this way is better. Alpha here, and then at the end under this isomorphism, I want to show the P and P check are the same. So let's see the reason. The reason is that let's say C 0 0. So I consider this double complex. Now this complex, I will take it to Xn X0 on. This is the inclusion. Omega 1 Xn. Maybe I just make some 0 omega 2 Xn. Blah blah blah. So this is here I will consider the inclusion. So let's call this one let's abbreviate this one to C, and then we have this inclusion of complexes. Okay, and it turns out that this is a quasi isomorphism. And remember, what is quasi isomorphism? It means that locally it must induce the isomorphism in cohomologies. Okay, here the cohomologies, even local, they are 0, but here local cohomology, what they are: exact holomorphic forms, closed holomorphic form divided by exact holomorphic forms. But if we take balls, small open set, it turns out that any closed holomorphic n form is exact in a small open sets of Cn. And that's why we have considered analytic, because we take local chart, and the local charts it will closed holomorphic form will be exact. At the end, if you take the cohomology here also, it is 0, you will get 0 to 0, which is isomorphism, except here, which will have this closed 0 forms are just constant, and we will have a C to C, and we will get the isomorphism everywhere. But one of the things that we proved, that any quasi isomorphism induces let's say is isomorphism in hypercohomology. H k omega xn, and this is the same as HK, the classical. It can be verified that the classical check cohomology. So we'll get this isomorphism xn. Okay, maybe let's. This one I write it as that. This is already a the Rham cohomology. H the Rham k xn. And now, it is. We are almost done. And this is remember that what it is. This, when you have this check cohomology element, let's say C, it goes to here where what is C0 0 0. So the isomorphism, if you write down explicitly, is given by this. So in the check cohomology representation of C, you put C on the top and the 0 elsewhere. And yes, once you know this one, then here, from here we have this HK map to X O XN. So this means that at the end of
we can see the
okay. So this is the map, and this is again so this, what is this map? This map is mean that whatever exists here, you just choose this guy, C. Of course, these are the representative. So, and I am not introducing new notation for C here and C here. Anyway, it turns out that so let's go back to this original problem. Okay, this map is induced by inclusion of C inside the holomorphic function, and this map was the projection. This P-check map was the projection on here after defining the Hodge filtration. And in some sense, so this is the, let's say this our projection P-check, and this is obtained by inclusion, which originates over this P map, and it is by definition it's clear that it is they are the same. Maybe this is one of the reasons that I have not up to I have to a little bit improve the proof. But the basic idea is this one. Oh, I am a little bit late. Okay, so once this is proved, then we reach the bottom of the proof of Lefschetz 1-1 theorem, and for this one, maybe let's go back to here. Okay, exactly. So our Hodge cycle is translated to something here. We prove that this guy goes to 0 here. So by the exactness of this long exact, so when this guy must come from some line bundle, and so this means that my alpha must come from some L. And it is well known that any line bundle is actually attached to a divisor, and then this Z is discovered in this way. And the proof finishes here. So maybe I say a few words more. So the basic part of the proof is this long exact sequence and the proposition that I mentioned. But something from our course point of view, the proof is not at all constructive. And the reason for this is this one. Once you go from here and you get line bundle, you can still express the line bundle, this Hij, explicitly. But the point is that why the line bundle is the divisors, is the line bundle attached to some divisor. This is not computational in the sense that if I give you explicitly some Hij, it is hard to construct divisors. And at some point I will mention this when we reach to Fermat variety and Hodge conjecture Fermat variety. What I am saying is still Lefschetz 1-1 theorem. From the computational point of view, it's a challenging problem. The proof is purely theoretical, and for constructing divisors and so on, it is kind of useless. And for this, we will be back when we are doing computation with the Fermat variety. Okay, I think I am done for today. Let me